All right, so we talked about this yesterday, definition of a limit. In mathematics, a limit is the value of the function as it approaches from the left and the right, not exactly what the value is. Like f of 3 is what the value is when x is 3. The limit as x approaches 3 is actually what it's approaching from the left and the right. That's it, not what the actual value is. Now, sometimes it is the value, right? Now, we talked about this where we said if your graph was like this, then as I'm approaching -3, let's say, from the left, it's approaching -2. From the right, it's approaching -2. So the limit as I approach -2 or -3 would be -2, correct? But also f of -3 actually is -2. Your limit and your coordinate are the same if it's continuous, right? The left and the right will be the same. So it's only when you get asymptotes, or points of discontinuity, where you might have a limit, but the actual value might not exist. So we talked about this one, and I said, okay, well, we have the limit as x approaches -1, and you factor the top, so we get x plus 1, x minus 1, and x plus 1 in the bottom. Now, the x plus 1 is my problem, because if I plug the -1 in, my denominator becomes 0, because x equals -1 is my non-permissible value. We agree? We also know that that non-permissible value is actually a point of discontinuity, because when they cancel off, we get the x value point of discontinuity, plug it back in, and we get our y. So actually, when we're getting the limit as x approaches -1 of a point of discontinuity, the y value is the limit, right? Because it's what it's approaching on both sides. So this cancels, and I'm back to, that is not true, the limit as x approaches -1 of x minus 1. Now, until I plug that -1 in, the limit has to ride along. We said that, right? That limit has to stay there until I plug it in. It's what tells you what the values are. And then I go -1, and I get -2, which matches. And we know that from 30-1, that is actually a point of discontinuity. In calculus, it's called a removable discontinuity. But we're not going to remember that word until February, because it'll mess us up. I'm just writing it here. I will never say it again until after February, which is at -1. Because we know that this is a graph that is at x minus 1. So we have the -1, we go up 1 over 1, up 1 over 1, down 1, left 1. That's the open dot. And we have this beautifully, perfectly straight line. We don't. But we said that the limit is what I'm approaching, not what the actual value is. So if I go from the left as I'm approaching -1, and the right as I'm approaching -1, they're both approaching -2, right? We talked about left bound and right bound limits, how we could write that. So we can say the limit as x approaches -1 from the left of f of x, but remember we have to state that f of x actually equals that function. We can't just say f of x but if it hasn't been stated. So let f of x equal this. So from the left, -1 is approaching -2, and then the limit as x approaches -1 from the right of f of x equals -2. And if from the left and the right they're approaching the same thing, then the limit as x approaches -1 of f of x equals -2. Yesterday I said if they don't approach the same thing, what happens? What if one approaches -2 and one approaches 3? Then the limit at that value doesn't exist. Does the left-handed limit still exist? Yeah. Does the one from the right still exist? Yes, but the limit at that actual value doesn't exist. And the graph for sure is not continuous because the left and the right is not approaching the same thing. So I said to you, if we can do it algebraically, always the best way, right? But our table of values will always work if we're ever stuck. For like, I can't get something to remove, I can't get a factor to cancel, I can't get the problem to go away, we can use the table of values. In this case, the table of values is kind of useless, because I'm going to show you. Is there a problem when I plug the 2 in? Do I have an issue? No. So some people are doing like all this crazy math, and they could literally just plug it in. So they could go limit as x approaches 2 of 2x plus 5, and then I say, hey, there's no problems. I can just plug it in. This is a linear function, right? 2x plus 5, that's a line. Are lines continuous? Yeah. And anywhere it's continuous, the function and the limit equal the same thing, correct? Whenever you're continuous, the function at that point and the limit equal the same thing. Because the right and the left, it equals the same thing, and at that point, it equals the same thing. So if you have a continuous function, you'll always be able to just plug in any value, because it's never going to have a problem, right? Your problems only exist where you have graphs where it's not continuous, like an asymptote or a point of discontinuity. So I could just go and plug it in. The moment I plug it in, the limit drops off, and I get 2 times 2 plus 5 is 9. So I know from the left of 2 and the right of 2, this is approaching 9 on the y. I also know at 2 it's 9. Why do I know that? Because I literally just plugged it in. I mathed it because of math. That was your reasoning? True. Because of math. If I just plug in, I actually did just find f of 2 as well, didn't I? Back here, I couldn't just plug it in the previous example because I had a problem. But when I plug it in, the limit is 9, the function is 9, this is a continuous graph. This is also something we're going to learn about continuity. We're going to learn that if the limit as x approaches 2 of 2x plus 5 actually equals f of 2, the graph is continuous. That's not 21. The graph is continuous. Because if your limit from the left and the right are approaching the same thing as that value, it's going to come from the left, it's going to fill in that value, it's going to carry on, right? Continuous. Come from the left, fill in the dot, carry on, right? The previous example, it came from the left, open dot, carried on. So it wasn't continuous, right? Because the limit and f of the limit as x approaches -1 and f of -1 were not the same value, so that graph's not continuous. That's how you prove continuity, is by showing the point and the limit are actually the same. So, talking about tables. Tables will always work. What you have to do is you have to pick values that get closer and closer to the value from the left and closer and closer to the value from the right. So I told you to type it into your calculator. So I'm going to do that again. Type it into your y equals. So I could type in 2x plus 5, and then I would go second trace value. It's a really large window. Second trace value, 1.99. Okay, 8.9. Then I do the same thing, second trace value, but now 1.99. 1.999, I mean. 8.998, you're going to start seeing a pattern. Second trace value, 1.9999. Weird. 8.9998. What do you think the next one's going to be? When I fill in 2, what am I suspecting I'm going to get? 9. I already cheated, and it's like I came to the movie and told you how it ended here, right? So it's 9. Then 2.01, what do you suspect is going to happen on that side?
0, 0, 2.
Yeah. So just a little above nothing, right? So, as we get closer from the left, do you see this? As we're approaching from the left now, this is really tight to the left. Like this is 1.9999 and 2.0001. Like we would have to zoom in really close to our graph to see actually what we're looking at right now. Now, if you did like 0 and -1, those are going to be substantially further away from 9, right? Because we're not getting right up close to it. So from the left of 2, I'm approaching 9. From the right of 2, I'm approaching 9. So I could say that the limit as x approaches 2 of x plus 5 is 9. I can show it with a table as well. Not even on screen. And then this one happens 2 is 9. Woo! It's a continuous function. From the left it's approaching 9, from the right it's approaching 9, at 2 it's 9. This baby just carries through, right? Continuous function. We're not going to worry about 9. These are like the homework questions. Now try problem 9. I'll explain that at the end. Okay. So one-sided limits. The left-hand limit x as c approaches -1 of f of x equals limit from the left. If it has a plus after the c, it's limit from the right. It reads the limit x approaches c from the right of f of x equals the limit from the right and the limit from the left, which we talked about already, right? Just putting that negative after or the positive after, that means from the left and from the right. Okay. Herein lies my issue. The last one I could have literally just plugged in, correct? Got an answer. Yes? Well, this one, if I just plug in 0, what happens? Got problems. I just said no. No. Exactly. We got problems. Okay, so I'm going to try and get the x to cancel off, which is what I did in that first example. And I can't. Okay, cool. Here I am. How do I solve it? What always works? Table, the longest convoluted method, which is the one they did first to prove that all the rest of this works. So, we're going to type this into our calculator. E to the x minus 1 over x. Everyone's typing it in. Make sure you put it in as a fraction. So if you don't have the fraction button, you have to put the numerator in brackets divided by the denominator in brackets. Now e, where the heck is e? E is the natural log. So remember how if I gave you log x, what base was it if it didn't have a base? 10. If I give you ln of x, that is actually the natural log. This I can be rewritten as log base e of x. And e is just like a non-repeating, non-terminating decimal. It's 2.7181, blah, 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 blah. It gets used in a lot of log questions, so that's why e has its own little button, just like pi gets used a lot, so pi has its own little button. So when we go to type it in, we're going to go, I'm going to do alpha link. You go alpha y equals. If you don't have that, you'd have to put this in brackets, right? Either way. So second ln gets you e. And you have to go e to the x minus 1 over x. It's second ln, the one below log. Make sure you use a -1, not a -1, because -1, if we thought this was a -1 sign, then you're actually doing e to the x times -1. That's why it doesn't work when people use a negative sign instead of subtraction sign. So, let's go back to here. Why did I pick these values for my table? Why did I pick -0.0001, -0.0001, and 0.0001? Why did I pick those? Because limit's approaching 0. I'm trying to get really close to 0, correct? So when I plug them in, I go second trace value, -0.01. Maybe I should type in the actual numbers. I don't know what. And I get 0.995. Okay? Then I type the next one in, second trace value. It keeps going. And then second trace value. Plug in 0, what happens? It says no thank you. Now remember, does the limit as x approaches 0 exist if from the left and the right it's approaching different things? If from the left and the right it's approaching different things, does the limit exist? If it approaches the same thing, does the limit exist? Can a left-handed limit exist and a right-handed limit exist, but the limit not exist? Yes. So let's look at this one. From the left, as I get closer and closer to 0, what does it look like I'm approaching? 1. From the right, as I get closer and closer to 0, what does it look like I'm approaching? So we can say I'm going to box this. Your questions are embedded throughout because your questions that pertain to the material you just learned. So if you're like lost and I don't know how to do this, look back. All right. Trig in calculus is never degrees, just so you know. Not a chance. Never has been, never will be. Your calculator always needs to be in radians. Okay? So we kind of like weaned you off of degrees in one semester, and now you have no degrees left. You're like, okay. So investigating a limit using a table in technology. Remember that that trig is always in radians in calculus. So we're going to investigate the limit as x approaches 0 of sine x over x using a table. So what do you need to put down here? Your own. Starts with a T, rhymes with fable.
Table.
It's table. Yeah, okay, you know this. Shh, don't ruin it for me. Can you guys do a table, please?
Wait, you said this like...
Okay, if you even just look at the graph of this one, what does it look like it's approaching? 1. It looks like it is, right? If we go to do our table of values, we would pick negative from the left and then the positives from the right, and it gets closer and closer to 1 on both sides, correct? And so we have the limit as x approaches 0 of sine x over x equals 1. So what we're proving is we can do some algebraic processes, but sometimes we might just have to go right back to the whole table thing to look at it. Okay? Now, at 0, does it exist? No. Does it look like it exists on your calculator? Yeah. The calculator does. If you look at it. Yours doesn't?
Yeah, I can see it.
You have the fancy new one. Yeah, these ones, they connect things. The TI-83s believe in life that everything is continuous. So they connect everything. They even connect rationals. If you look at someone who has a TI-83, they'll have like their graph, their rational graph will look like this, and then they'll connect, and then they'll go like this.
It's better. It makes it obvious very quickly.
No, it's not better. It's like wrong.
It's better than
It's better like that. When it's wrong, when it's wrong, it's actually
Because
better.
it's easier to look at. It's an additional feature. It draws your attention.
It didn't draw the asymptote. It looks like the graph. It's actually connecting those, just so you know. It feels like it needs to connect.
But
Peter's selling his calculator. It's perfect. It's right.
Perfect.
It's great. You know how many people with TI-83s connect them?
I don't.
Too many. Too many.
I would not.
Good. You should. All right. Here we are. Investigating a limit using a graph. So we're looking at this. This here is the graph right here. This is the graph of f of x, and here's a closed dot. Do you see that? That graph is said to be continuous. We agree? So we are looking at the value of c. The c is the x value. Instead of like 7 or 8 or 9, our x value is c. And in university, often, your everything will be proved by variables, not by saying, oh, this works for 3 and this works for 4, so now it works for everything. They'll often do theorems or proofs to show that it works with the value of c, or x, or m, or whatever it may be. Now, for this one, if I look up here, c, they're just, this little drawing here just says that at c, my y is L. We agree? That's all that's saying. So here it says f of c equals L. Is that a true statement? Yeah. F of c equals L means at the dot, there's a closed dot, it's f of c equals L. We agree? What would the limit be? The limit as x approached c of f of x, of this graph. It equals L. Because from the left, from From the left, it's approaching L. From the right, it's approaching L. So the limit at C is L, right? Now, I have f of C equals L, and I have the limit equals L. What can you tell me about this graph? It's continuous. You've already done lesson 4. You just don't even know it yet. Lesson 4 is about continuity. It's literally proving this, what we're talking about today. So when you get to that lesson, you're like, well, this is easy because you've learned it already. Okay? Now, what's different on this? This is the graph of g of x. So g of x, actually, this is the graph. It goes like this. It has an open dot. It goes like this. It has a closed dot up here if you didn't notice it.
What does that open dot mean?
That's just the,
I mean, no, like the closed dot.
that's the coordinate at C. Remember, you guys have piecewise functions in the world. You just don't deal with piecewise functions until you hit calculus. If you were TI-83, you connect that dot. You're right. Okay. So, does G of C equal L? No. Here's L. Here's C. G of C actually equals G of C. Right? G of C does not equal L. This is a true statement. But, what about my limit as x approaches C of G of x? It still equals L because from the left, I'm approaching L. From the right, I'm approaching L. What can you tell me about this function, though? It's not continuous because C, G of C is G of C in this case, and the limit actually equals L, right? Those are not the same, so therefore it's not continuous. Okay, so that one always throws people for a loop because you haven't seen graphs with piecewise functions where they fill the dot in above. This one's more like your life. This is more where you've been sitting. So this one goes, and then, sorry, I don't mean to have an error. The graph draws, and then here's an open dot. And there is no value for C. H of C is actually not defined, right? H of C doesn't exist on this graph. It's a gap. It's point of discontinuity. Removal discontinuity. Remember I said I wasn't going to talk about that stuff? It's point of discontinuity is that open dot in between. Okay? Does my limit exist for H of X? Yeah, from the left it's approaching L. From the right it's approaching to the limit as X approaches C of H of X equals L. Now does H of C equal H of L? Or the limit of C? Limit as X approaches C of H of X? Do they equal? No, there's actually an open dot. So can the graph ever be continuous if there's an open dot at your limit? No. Because it's not continuous, blatantly. Like with your eyes, you can see it's not continuous. Okay? So we talked about this. We talked about that. We wrote it on there. You can write it down here if you'd like. So this suggests that the limit of a function as x approaches c does not depend on the value at c or lack of value of c at all, right? We don't actually care what the value is. This is what I'm trying to, literally trying to, so a limit is not actually a value. It's how it's approaching. And as long as you can think a limit is what it's approaching. If you Google, what is the limit? It'll say what it's approaching. That's the very first part of what it'll say in every single definition. They'll have the word approaching in it because it's what you're approaching from the left and the right. Okay? Not the value at it. I don't actually care what the value is until I talk about continuity. So, welcome to piecewise functions. You've talked about piecewise functions before. When we did absolute values in grade 11, when you did absolute values in grade 11, it was actually two lines. One was a negative slope line, one was a positive slope line on both sides of it, and then you could write it as a piecewise function. For the domain of this, it's this negative slope. For the domain of this, it's this positive slope line, etc. This one here wants us to use the graph to investigate it. So it's saying, okay, we have a graph, it's f of x. F of x actually has two pieces to it. Here's two pieces to the puzzle. This will explain how the heck they're maybe getting that other graph that you guys like, what is this? Okay, so we're going to draw ourselves a straight line. So what I always want to know to help myself out is, for example, the first one says 3x plus 1, but it can't equal 2. So I need to draw a point there. I need to draw an open point there, correct? So I still find the value. So I'm going to go 3x plus 1, but I'm going to fill in f of 2. Now people will say, but it doesn't equal that. That's great. I'm going to fill it in, and then I'm going to do an open dot there, right? Because there would be an open dot at that spot. So I would go 3 times 2 plus 1, so it actually equals 7. So at 2 and 7, oops, I stopped counting. I actually have an open dot because it can't exist there. We agree? So when I say it can't exist there, I'm like, okay, well, I'm finding it, and then I'm saying it can't exist there by doing an open dot. Now I can use any values. I'm going to draw this. This is 3x plus 1. Could I fill in a whole bunch of values and figure it out that way? Yeah, is that the most convoluted method? Mm-hmm. You can draw lines. I believe in you. We learned about them in grade 10. We kind of carry them through. So with lines, what we do, and this is, oops, come on. Okay, this is a 2 in here just so you can see it. Okay, so with lines, this is my starting point. It's my y-intercept. I always say when you draw lines in grade 10, you're literally like someone's giving you a map. Okay, and they're saying, I'm starting at 0, 1, and then from there, I'm going to go up 3, right 1 to get every single point, or the opposite, down 3, left 1 to get every single point, right? When you're drawing lines in grade 10, it's literally like a little finding map. Here's your starting point, now carry on. So my starting point is my y-intercept, which is at 1. But my y-intercept is actually the coordinate 0, 1, because remember it's a coordinate. We go to 0, 1, and then we use the directions that they give us. Oh, up 3, right 1, up 3, right 1, up 3, right 1, up 3, right 1. So we're going to go up 3, 1, 2, 3, right 1. Up 3, 1, 2, 3, right 1. Oops, can't fill that one in. Up 3, 1, 2, 3, right 1. So it's here. And then how do I go the rest of the way? I can do the actual opposite, because this could be negative 3 over negative 1. I can go down 3, 1, 2, 3, left 1. Down 3, 1, 2, 3, left 1. And then pray for me as I try and draw a straight line. There's a graph that I just made. Oh my gosh, I would use a ruler if this was real. Please make sure it's straight. It's straight. It's totally straight. It's totally cool. It's perfect. It's great. It's not great at all. It makes me kind of want to cry. I would give myself crappy marks. What are we missing? The second one. The second one just says when x equals 2, the graph is 10. Well, that's actually just a coordinate, right? When x is 2, y is 10. That's all I get. X is 2. This is just my y. X is 2, y is 10. Okay, cool. You see now how I could get that other graph that they had drawn back when? It's just a piecewise function. That's all it is. This just means 210. So here it wants you to determine the value of f of 2. What is the value of f of 2? It's 10.
What kind of equation would you need to get a graph of x?
This. You have to get it written. This is the equation you would need. This is the equation.
That's the equation.
Yeah, it's a piecewise function. It says for the graph of f of x, I need to draw this. When it doesn't equal 2, I need to draw this when it does equal 2. Here's my graph. This is, in its whole entirety, the graph of f of x, including that blue dot. It's saying f of x equals these two pieces drawn together. It's just a piecewise function. Piecewise functions can have numerous functions. They could have a whole bunch. They often max out at 3 for us, but they could just be like, and from here to here, I'm going to draw this. And from here to here, I'm going to draw this. And at this point, I'm going to have this. From here to here, I'm going to draw this. You have like a line, like a parabola, and cubic function, exponential. Yeah.
Are we able to write piecewise functions in our calculator?
Yes, you can.
Well, somebody who doesn't have the fancy one?
Yeah. No.
We are? No? Okay.
Well, you can write them in as pieces. Like you could just put them in as pieces and it'll draw that graph. You put this into y1, put that into y2. The catch is you can't limit it.
And you can't have a restricted domain. You can't.
Well, you'd have to actually put behind it the restricted domain.
Yeah.
Like you put the squiggly bracket restricted domain behind it. But I'm not sure which calculators allow it and which ones do not. Some do, some do not. You can test it out. But guess what? This is often on a non-calculator section. You don't need a calculator for this. Now it wants the limit as x approaches 2 from the left. What would it be? From the left, it's approaching 7, yeah. And then the limit as x approaches 2 from the right. Also 7. But from the left, it's approaching 7. From the right, it's approaching 7, right? Here's 7. So what can we say about the limit as x approaches 2? It's 7, because they're the same. Can we say this graph is continuous? First off, it doesn't look very continuous, right? But what we can say is, yeah, that's just a caveat. So we can say that the limit as x approaches 2 of f of x does not equal f of 2. Therefore, the graph of f of x is not continuous. And then this was another little side. If there is no single number from the left and from the right, the value of f of x approaches as x gets closer to c, we say that no limit as x approaches c, or more simply that the limit of f of x does not exist at c. And then here's this. Now I'm going to explain to you how this works, these questions. In your section 1.1 of your textbook, there's questions, and then there's AP questions behind it. If it says try AP practice problem 4, it's number 4 out of the AP practice problems. If it just says try question 12, it's out of the questions. And it's in section 1.1, okay? Don't worry about working on them until we're done it. It's not a big deal, but I'm just explaining to you. If you wanted to, that's where you could go to do them.